Physics is such a broad area of study. It covers practically anything and everything in the universe. This year we explored areas such as kinematics, dynamics, force fields, gravity, and electromagnetism. What you don't know is that this can all be applied to a field of study known as particle physics. Particle physics is a branch of physics that deals with the properties, relationships, and interactions of subatomic particles. This all leads to our topic, which is the particle accelerator.
Particle accelerators. But what are they? The history of particle accelerators. Particle accelerators were first developed by two scientists named John D. Cockcroft and Ernest T. S. Walton at the Cavendish Laboratory in England. This type of accelerator consists of a multi-step voltage divider, which accelerates ions linearly through constant voltage steps. The device bombarded lithium with accelerated protons, being the first to produce an artificial nuclear disintegration.
Particle accelerators are an apparatus designed to accelerate subatomic particles to high velocities by means of electromagnetic fields in order to collide with other particles. There are two main kinds of particle accelerators: linear accelerators and circular accelerators. Since the 1930s, particle accelerators have played a crucial role in helping physicists build and strengthen a theory that helps explain the subatomic world around us. It's called the Standard Model of particle physics. The Standard Model essentially states that everything in our universe is made up of a few fundamental particles governed by four fundamental forces. These particles split into two groups, quarks and leptons, which combine together to make the atoms which we are all familiar with. The problem, however, comes with the second part of the Standard Model, which states that force carrier particles, bosons, help explain how matter interacts with the fundamental forces. To date, we know of three bosons. The first one being the one that interacts with the strong nuclear force field, the gluon. Second, the one that interacts with the electromagnetic force field, the photon. And lastly, the one that interacts with the weak nuclear force field, the W and Z bosons. The problem, however, is we still haven't been able to explain gravity yet. We just haven't found the boson yet. To add, the Standard Model works well on the microscale, however, it doesn't fit the macro scale. Physicists have found it really difficult to encompass the existing quantum and general relativity theories into the single framework of the standard theory. This is where particle accelerators have been playing a crucial part in furthering our research and solidifying our understanding of the Standard Model.
Particle accelerators used in everyday life. We can use them for semiconductors, clean air and water, nuclear energy, shrink wrap, and even cancer treatment. Shrink wrap. How does it work? Heat shrinkable film, also known as shrink wrap, is made of polyethylene plastic. The plastic molecules are called polymers. They are long chains of carbon atoms stuck together with two hydrogens attached to each atom. However, when hit with a beam of electrons from a particle accelerator, the plastic's polymers strings become chemically active. The electron beams knock off the hydrogens from the carbon chain, and the empty spaces left are filled with other carbon chains. What is left are long chains of carbon, which are extremely strong together. And with this, the plastic becomes elastic, and food companies purchase this in order to wrap their products. Cancer treatment. This is Bob. Bob has cancer. He must undergo treatment from a particle beam where the electrons directly attack the tumor on the surface of his skin. After many treatments, Bob no longer has cancer. With the use of a particle beam, there are very few side effects, it is a much healthier form of treatment, and it kills the cancer faster.
All particle accelerators essentially work in the same way. To start, electric fields strip hydrogen atoms of their electrons, leaving behind just the protons. From there, electric fields consistently flipping from negative to positive frequencies will help propel these protons forward. At intervals, radio frequency cavities allow radio waves to interact with these high-speed particles to provide even more kinetic energy. Quadruple magnets are often used to help focus the particles together in groups to increase the chances of collision. Once a collision occurs, particle detectors placed around the collision site are then used to monitor resultant particles. The difference, however, comes when examining linear versus circular accelerators. In linear accelerators, the electromagnetic force simply helps guide the particles straight forward to collision. However, in circular accelerators, the magnetic force runs perpendicular to that of the velocity of the particle, resulting in a curved motion. This is done using dipole magnets. There is so much value in the research done using particle accelerators. The LHC started a physics run on May 23, 2017. The previous run alone collected a massive amount of data of over 6.5 billion collisions. Colliding multiple particles together allows us to create and discover other rare particles such as the Higgs particles, or perhaps even discover the root of some strange new phenomena. Another future project is the International Linear Collider. The ILC is a proposed linear particle accelerator that will collide electrons with positrons. It is planned to be up to 50 kilometers in length, making it the longest linear accelerator if successfully completed. The project is huge because once the accelerator is completed, it will most probably expand on the information of the effects of physics that the standard model describes. Alternatively, there is another project proposed in case the ILC doesn't go through. The Compact Linear Collider, or the CILC, is designed to accelerate both electrons and positrons, as well as collide them together. Instead of continuing design on both projects individually, the ILC and CILC were joined together to form one huge project known as the Linear Collider Collaboration, or the LCC. Now the two projects can be worked on simultaneously, and they are much better organized, meaning that the future of particle accelerators is pretty bright at the moment.
THANKYOU,